Hello and welcome to another lecture of Introduction to Astrophysical Fluids. Previously, we derived both collisionless and collisional Boltzmann equations. Today, we will learn how to derive the moment equations starting from these equations. Okay. So, as I said that we have already derived the collisionless and the collisional Boltzmann equations, which should look like this. So collisionless equation, you have del F del T plus U dot nabla F plus A times A, scalarly contracted with a gradient in the velocity space, which is acting on the F, which is the distribution function, is equal to 0. Okay. And in case of collisional systems, we have the same thing in the left hand side, but the right hand side gives us a collision integral, which symbolically we just write some curly delta F curly delta T and with a subscript collision. And we know that for normal elastic binary collision, which is a very simplistic case, but which is somehow very reasonable for microscopic cases. Okay, for example, the kinetic systems of gas molecules. Okay, so for this, the collisional integral term should look like this. Okay, this one. That is integration over d cube u1 integration sigma omega d omega u minus u1 modulus if one prime minus if1. Okay, once again the primed coordinates are the distribution functions after the collision and the unprimed are the distribution functions before the collision. Okay, so here you can again, just for reminder, as a reminder, like A is the acceleration and this is nothing but the body force by the mass. Okay, mass of one particle. Now, as I just said, that both these equations 1 and 2 are in general giving the evolution equation of F. Okay, that you can see here. And therefore, they are the equation of evolution for the kinetic level, right? As I just, as I said in one of the previous lectures actually, that we are actually trying to develop dynamical theory at different levels. So it is the kinetic level kinetic level equation of evolution. So we need for every dynamical system an equation of evolution, and of course before that we need a well-defined state. Okay, so this is the equation of evolution. Now the question is that we all have this, and as I just promised that in this lecture we will basically learn how to obtain the moment equations. Okay, so that is something we have to now learn. Okay, so for that we first have to define what moments are. So in the present context, moment means simply velocity moments, and velocity means kinetic velocity, that means u. Okay, so a statistical moment of order j for velocity is simply defined by mj, which is a function of r and t, that means only space and time, that will be simply equal to integration in the velocity space f times u to the power j. Okay, so this is a vectorial j, so that means if it is like let's say u cube, then this is nothing but u tensorial u. Okay, so this is the thing, and so that is integrated over the velocity space, which is normalized by f d cube u. Okay, and already during the derivation of Liouville's equation we have learned that this is nothing but the number density, right? So every time for the normalization, every averaged quantity should be normalized by, or should be divided by the number density in order to get the normalized value of the statistical moment. Okay, so a moment equation is nothing but an evolution equation of the velocity moments of different order. So this is the moment of order j for the for the velocity, kinetic velocity. Now a moment equation is nothing but the equation which involves the ddt or the del t of this mg. Okay. Now let us again write down the proper definitions of different moments of the velocity. So for m0, you can easily understand that this is simply u to the power 0, that will be 1. Okay, and so it will be, so then this will be the, both the numerator and the denominator, they will be the density, number density. So this will be 1. So when I just say 1, that means you can actually, instead of using 1, you can use any arbitrary constant. Okay, m1, which is the which will be obtained if we put j is equal to 1. So it will be simply integration f u d cube u divided by n, and which is nothing but the average value of u, and this is known as v. Okay, so average value of u, we will call it v. Okay. And actually you will understand later that v is something which is similar to the macroscopic velocity. Okay. Then what is the moment of the second order? As I just said, that will be simply nothing but the average of u tensorial u. Moment of third order, for example, you know now, that will be the average value of u tensorial u. Once again, when I use this angular bracket symbol, that simply says that this, for example, this says that this is integration in the velocity space f u tensorial u d cube u by n. So if I just want to hint at this integral, that will be n times this angular bracketed thing. Okay, so that thing should be clear. Okay, I am not sure whether it was perfectly visible. So once again, so the angular bracket means that the integration of that quantity, okay, along with the distribution function in the velocity space divided by the number density. Okay, now let us write the definitions accordingly, and for that we can easily say that, as our also previous knowledge says, that f d cube u is nothing but the number of particles per unit time per unit volume. So only f is nothing but the number of particles per unit volume, per unit time per unit phase space volume. Now when you integrate this in the velocity space, then it will simply be the number of particles per unit real volume, and that is nothing but our particle density or number density n. Okay, then what is u? Already I defined, this is v, and that should look like this. Once again, u tensorial u averaged, so this is 1 by n integration u tensorial u f d cube u. Already I discussed about these things. Now this thing, this mn times u cross u. So one thing you should that should be clear, that u tensorial u, for example, should have a dimension, inside the angular bracket should have the dimension of u square. Okay, so mn u tensorial u angular bracket, okay, is nothing but the n is the number density, m is the mass of one particle, so this is the mass density, this is the mass density. So mass density times u square, so you can easily understand this is nothing but something like volume density of energy. Okay, and you can actually check in the standard literature, this is known as the momentum flux density tensor. Okay, momentum flux density tensor. Okay, so because momentum is nothing, the density of momentum. So basically, if you see that the density of momentum is nothing but roughly mnu, and when this is somehow multiplied, of course here it is tensorily multiplied, but somehow multiplied with another velocity, it gives you the corresponding flux density type of thing. Okay, and this is equal to this. Once again, this is the definition, and this is the standard second order moment for our case. Okay. Now, in order to obtain a general jth order moment equation, that is an equation containing del mj del t, the straightforward way is to multiply both sides of 1 and 2. 1 and 2, just for recapitulation, are nothing but the collisionless and the collisional Boltzmann equations. So we just have to then multiply both sides of those two equations, okay, by this corresponding mj, and then we have to integrate that in velocity space. Okay, so I mean, not really, just a minute. So here you can easily see, so it is not really mj, but I mean, maybe I have to be a bit more clear. So it is not mj, but I have to say I mean just uj, sorry, to say uj. First we have to multiply by uj and then to integrate in velocity space. Okay, because mj is already integrated, so that is not the correct thing, sorry. Okay, so this is, again, it is written wrongly, so this is not the correct thing actually. According to the definition, it should be simply uj. Okay, so then multiplied by this equation, and that is equal to 0. Okay, because I mean okay, so as you can easily understand that for collisionless case, that's written here. So to perform the above action which I prescribe here is very direct and very easy for one, that is the collisionless Boltzmann equation. Okay, and because the right hand side is 0, so if you just multiply something with this, that will be 0, and then you integrate over a closed volume, then that will also give you 0, and then the I mean the corresponding moment equation should look like simply integration u to the j, the total left hand side of collisionless Boltzmann equation is equal to 0. Okay, so for the collisionless case, 0 is guaranteed, but for the collisional case, the right hand side is 0 only for special case. In general, the right hand side for collisional case, I mean, so once again, the right hand side is not 0. Okay, is not 0 for collisional case, and we have a term like we have a term like u j. Okay, yeah, so that is the correct expression, as you can see. Okay, so it is evident that anything or any function can be multiplied to the LHS of collisionless Boltzmann equation, because the RHS will also always be 0. Okay, and then that will be easier to handle, because you see that the collision integral itself is not a very simple quantity. Okay, so when you have the collision integral for something where you know the system, that means you just have binary elastic collision, that's okay, or in any other simple case where you have known models, that's okay. But in an arbitrary case, it is not really a guarantee that you can always model the collision integral sufficiently or sufficiently accurately. Then what happens, that I mean the analysis is incomplete, so you cannot proceed further. So that's why it is good that in some sense, if the right hand side is already 0, because so the left hand side is somehow known, but the right hand side is not always known. The right hand side is known only for binary elastic collisions and some very limited cases. Okay, So in the next part, you will see that there is a, I mean, for some cases, okay, for some cases the right hand side basically becomes 0. Okay, so for collisional systems, the RHS is not automatically 0. However, if we multiply both sides of the collisional Boltzmann equation by a variable, okay, chi, just remember, which is an independently conserved quantity in an elastic binary collision, for example. So even for elastic binary collision, you know, like integrating the total collision integral is not trivial. So for example, at least the challenge is that at least for binary elastic collision, can we do something so that the collision, we can get rid of the collision integral. Okay, so but once we know that, then you know, like we can actually try to incorporate this for any arbitrary interaction as well, so that we then always will search for some variables which are conserved in this type of interactions as well. Okay, now whether this is always equally easy or not, that is a question. Okay, now at least for binary collision, how to handle how to get rid of the collision integral in the moments equation, then the answer is that if we multiply with some independently conserved quantity, let's say chi, you know, for example, they are nothing but, for example, the numbers, the components of velocity, the kinetic energy, okay, and then integrate in the velocity space, then we get something very interesting for the RHS. Why? Because then the RHS becomes simply that I call I, simply in blue, which is nothing but an integration in the velocity space chi times curly delta f curly delta t collision d cube u is equal to, now you write the whole expression for the collision integral times chi. Okay, now just by observation you can easily check that this integral I, which I have written over here, just becomes this. Okay, this one. If you simply swap chi by, swap between the u and u1. Okay, then what happens? Of course, all the u will be u1, and then chi will be now chi1. Okay, because chi1 is nothing but chi of u1. Then f will be f1 and f1 will be f, and same thing for f1 and f prime and f1 prime. Okay, now so in this integral I simply blindly, because this is an integral where the integration is done on both u and u1 space, then I can just say that if I interchange between u and u1, nothing will change in the final value of the integration, right? Now I can easily say that I will now say my u1 will be u and u will be u1. So then the one thing I have to check, that what will be the change in this. So d cube u1 and d cube u, if they are changing, no problem, because integrations on both the space. This one will also not change, because this depends, if you remember the previous discussion, depends on the set of initial velocities u and u1. Okay, so a swapping between them cannot change sigma omega d omega. Okay, remember when we were deriving the collision integral, we talked about this. Okay, and what about u minus u1 modulus? This is also cannot be changed because there is a modulus, so that will be then modulus of u1 minus u, which is the same. Okay, here if you just change between the f and f1 and f and f1 and f1 prime and f prime and f1 prime, nothing will change. So finally your the I will be the same. So this will be look like this. Okay. So as both are I, so I can be now written as half times. Oh, what happened? Half times, okay, a sum of these two integrations. Okay, and that means that all the other factors are common. Only I have a sum of chi and chi1. Okay. Now, in the next step, we perform another swap between the unprimed and the primed variables. Okay, and that means that before collision, the variables will now be primed, and after collision, the variables will be unprimed. Okay, this. We also suppose that in our case, the elastic collisions are usually reversible in nature. Okay, so that's why they are, the collisional cross section or this sigma omega d omega will not change. Okay, so if I simply say that if I just swap between primed and unprimed coordinates, then I can again be blindly written as this. All these quantities inside, they're just the dummy variables. Okay, now if they're the dummy variables, basically, then you can simply say that, actually they are dummy variables in the sense that it is true that only this u and u, the quantities on which the integration is done, they are dummy variables. But okay, here one thing is very easy to understand, that you have this expression for I. Okay, now you can simply say that I am studying the reverse collisions. So I am simply saying that I am just trying to change trying to do the same type of integration for the reverse collision process or inverse collision process. Then this will be u to u prime, u1 to u1 prime, that will be sigma prime, okay, that will be omega prime, and that will be u prime minus u1 prime, and this one will be f1 minus f prime f1 prime, and this one will be chi prime, and that's what I have written over here. Okay. Now check that according to the reversibility, this part will be unchanged. This part will be unchanged, as we already discussed that in a binary elastic collision, the relative velocity before and after the collision of the two particles, they are the same. Okay, that is again the same thing of saying the coefficient of restitution is 1. Okay, this term will change its sign, so it will become negative. Okay, so f1 minus there is a, so I have to write this clearly. F1 prime will now become f1, just a minute, no, I think this is correct. Yeah. Yeah. Okay. So this is the thing. Okay. So this is nothing but minus of f prime f1 prime minus f1, and now the chi will be replaced by chi prime. Once again, chi prime is nothing but chi of u prime. Okay. So this is nothing but the same thing. So the rest part, so this part has changed its sign. Okay, that's why this minus has come over here. Okay, this minus sign. This chi is replaced by chi prime. This is okay, this is unchanged, this is unchanged. Now what about this part? Remember when we were talking about the derivation, we were deriving the collision integral, we said that if we suppose that the two particles which are colliding, then during the collision, okay, or rather at the moment of the collision, basically, if the two particle system who are colliding, okay, So two particles who are colliding, if we assume that at that point when the collision takes place, there is no other interaction other than the force of collision, okay, experienced by those two particles, then for this two particle system we can define a Hamiltonian system. And if we can define a Hamiltonian system, then for that two particle system we can apply the Liouville's theorem. And then again, just remember the corollary of the Liouville's theorem for this two particle system, where you can have this d cube u prime d cube u1 prime will be equal to d cube u1 along a trajectory. Okay, so that we can use. If we can use that, then simply you can write that I is now equal to minus, everything is the same, okay, of the original I, but only this one is replaced by chi1 prime. So there is a minus which is new, and the chi is now replaced by sorry, I am here. Chi is replaced by chi prime. Okay, there is a minus and chi is replaced by chi prime. Again, we are always being in the direction of the inverse collision. If we now change between u prime and u1 prime, then there will be actually no change. So from the original I, we again have this type of expression where we have a minus sign due to this factor, okay, and this multiplicative variable will be then chi1 prime, which is nothing but chi of u1 prime, okay. So finally, as all of them are equal and equal to I, then you can write I is equal to 1 by 4 integration d cube u1 integrated over both the spaces, integration d omega sigma omega modulus of u minus u1 f prime f1 prime minus f1, okay, times this factor chi plus chi1 minus chi prime minus chi1 prime. You see in the deep green color the total expression, and this is the expression for the collision integral when it is multiplied by something which is conserved in a binary elastic collision. Actually, the collision need not be binary elastic. Now the thing is that if you have an arbitrary collision, just if something which is defined in the is conserved in that collision, then actually you can search for this type of thing. Of course, you have to be careful that all the type of intermediate suppositions or hypotheses, they are also satisfied. For example, whether you can apply this type of intermediate Liouville's theorem for two particle systems or not. Okay, this type of thing. So this is subtle, but now for our present case, you can simply say that this is the collision integral, when this is multiplied by something which is a conserved quantity of a binary elastic collision and then integrated over the velocity space, okay, gives us an expression which looks like this, and this one, due to the conservation, vanishes. Okay, this is the conservation. So finally I can say that the integration, that the integration will vanish. Okay, so although in collisional Boltzmann theorem or Boltzmann equation, the right hand side is not 0. Okay, for binary elastic collision, at least the thing is that when we are trying to derive the moments equations, okay, then if it is a moment of if the moment, or which is a velocity moment, is conserved in a binary elastic collision, then after integration the right hand side is vanishing. That's why we have we finally get rid of the right hand side, okay, in the moment equation. So for collisional moment equation, what I just said, okay, the right hand side vanishes only when the corresponding moment is a conserved quantity of binary elastic collision. For example, number, which is nothing but the velocity to the power 0, component of velocity, which is nothing but a corollary of the conservation of momentum components. Okay, here this is just the component of velocity, because in microscopic case all the gas molecules, they have the same mass. Okay, or gas molecules, or any molecules, okay, system molecules. Then U square, this is also another thing which is coming from the kinetic energy conservation. Okay, so if we multiply for collision-less Boltzmann equation, this is always 0. For collisional Boltzmann equation, the right hand side is 0 only after integration if they are multiplied by this type of things or any other conserved quantity of a binary elastic collision. Okay, so in the next part of the lecture, we will try to derive directly the moment equations. Okay, thank you.